deep beneath the quiet border of France and Switzerland, below green fields, sleeping villages, mountain roads, and the soft edge of the Alps, there is a circle hidden in the dark. It is not a tunnel for trains. It is not a bunker. It is not a secret military base. It is a machine built to listen to the smallest things in existence. A ring of metal and magnets, buried underground, stretching for miles beneath Europe. A machine so large that it crosses from one country into another. So cold that parts of it are colder than deep space. So precise that it can guide particles smaller than atoms around a giant underground circle, again and again, until they are moving almost as fast as light itself. And then, at just the right moment, it makes them collide. Not once, not twice, but again and again and again. Millions upon millions of invisible impacts happening in the dark every second. To most of us, this sounds like destruction, like scientists taking the building blocks of matter and smashing them apart just to see what is inside. But to the people at CERN, this is not destruction. It is a way of listening. Because when particles collide at nearly the speed of light, they leave behind clues, tiny traces, brief flashes, curved paths through giant detectors, patterns so delicate that no human eye could ever see them directly. And inside those patterns, physicists search for something extraordinary. They search for the hidden rules of reality. For more than half a century, those rules have been described by one of the most successful scientific theories ever created. It is called the Standard Model of Particle Physics. The name sounds plain, almost boring, but the idea behind it is anything but boring. The Standard Model is the rulebook for the very small. It tells us what matter is made of. It tells us how tiny particles interact. It explains why atoms can exist, why light behaves the way it does, and why the invisible world beneath everything around you is not chaos, but order. Again and again, this rulebook has been tested. Again and again, it has survived. Scientists predicted particles before they were found. Then machines were built powerful enough to look for them. And there they were, waiting in the data, almost exactly where the mathematics said they should be. That is what makes the Standard Model so powerful. It has been right so many times that when it seems to be wrong, even slightly wrong, the entire world of physics pays attention. And that is where our story begins. Not with an explosion, not with a black hole, not with a portal opening under Europe, but with something far quieter, a number, a tiny measurement inside the death of a particle that lived for only a fraction of a second, and then fell apart in a way that did not seem to follow the rulebook perfectly. At first, the difference was small, so small that it could have been nothing, a statistical accident, a shadow in the data, a strange little fluctuation that appears for a moment and disappears when scientists look more closely. That happens in physics. The universe is noisy, experiments are hard, and when you measure millions or billions of events, strange things can appear simply by chance. So the scientists waited. They gathered more data. They checked again, and the strange number was still there. Years passed. More collisions were recorded. More particles were studied. The analysis became sharper. The detectors improved. The calculations became more careful. And still, the strange number did not quietly fade away. It remained. Not loud enough to declare a new discovery. Not clear enough to rewrite the textbooks. But too persistent to ignore. Like a soft knock coming from behind a wall. Not once, not twice, but again and again in the same place. Somewhere inside one of the rarest particle decays ever measured, something seemed to be leaning away from the prediction. Not by much, but in physics, sometimes the smallest lean is where the biggest discoveries begin. A star does not need to move very far to reveal the gravity of an unseen planet. A door does not need to swing wide open to prove that something pushed it. And a particle does not need to break the laws of physics completely to suggest that the laws we know may not be the whole story. This is the mystery at the heart of CERN today. A tiny signal beneath Europe. A strange pattern in the way a particle dies. A possible crack in a rulebook that has stood for 50 years. And the most unsettling part is not that scientists have no idea what it means. The unsettling part is that they have several ideas, and none of them are simple. It could be nothing. A ghost in the data. A trick of statistics. A hidden flaw in the way the prediction is calculated. A reminder that even the sharpest tools in science can still be fooled. But it could also be something else. Something deeper. A new particle that cannot be seen directly. A new force, too subtle for ordinary matter to notice. A hidden layer of reality, pressing gently on the particles we do understand, leaving behind only a faint distortion in the pattern. If that is true, then the machine beneath Europe may have already caught the first hint of physics beyond the standard model. Not a confirmed discovery, not yet, but a clue. And in science, a clue that refuses to disappear can be more powerful than a shout. Tonight, we are going down into that tunnel. We are going beneath the fields of Europe, into the cold ring where particles circle in darkness. We will follow the protons as they race near the speed of light. We will step inside the detectors that catch the invisible wreckage of collisions. We will meet the rulebook that explains almost everything and the mysteries it still cannot touch. We will watch a short-lived particle appear, tremble, and vanish. And we will ask why the pattern of its death has made physicists look again. Because this is not a story about CERN destroying the world. It is not a story about fear. It is a story about something much stranger. The possibility that reality is whispering. And for the first time in a long time, the rulebook may be listening. To understand the signal, we first need to understand the machine that heard it. The Large Hadron Collider does not sit above the world like a rocket, a telescope, or a great radio dish pointed at the stars. It hides beneath the ground. About 100 meters below the surface, under fields and roads and quiet European towns, there is a circular tunnel almost 17 miles around. If you could walk the entire ring, step by step, you would pass under the border between Switzerland and France, moving through a buried loop, so large that the landscape above it barely seems to notice. Cows graze above it. Cars drive over it. People sleep in nearby villages, unaware that below them, in a tunnel colder than the darkness between stars, some of the smallest pieces of matter in the universe are racing in circles. The machine is called the Large Hadron Collider. Large, because it is enormous. Hadron, because it works with particles like protons, which belong to a family of particles called hadrons. Collider, because its purpose is simple and almost brutal. It makes particles crash. But the simplicity ends there. A proton is already impossibly small. It sits inside the heart of an atom, and atoms themselves are so tiny that millions of them could fit across the width of a human hair. Yet inside CERN, scientists take these tiny protons and guide them around a giant underground ring, not once, but thousands of times every second. They are not pushed by wheels. They are not carried by wires. They are controlled by magnetic fields. All around the tunnel, thousands of powerful magnets bend and steer the proton beams, keeping them locked inside their circular path. These magnets are not ordinary magnets. They are superconducting magnets, chilled to temperatures colder than outer space, so they can carry enormous electrical currents without resistance. The machine must be cold because the energy inside it is extreme. It must be precise because the particles are almost unimaginably small. And it must be huge because to look deeper into matter, scientists need more energy. So the protons circle. Faster and faster. Closer and closer to the speed of light. In one beam, protons race one way. In another beam, protons race the opposite way. For most of their journey, they pass through separate pipes, moving in darkness, guided by invisible force. But at certain points around the ring, the beams are focused until they become thinner than a human hair. Then they are aimed directly at each other. And there, inside the heart of giant detectors, the collisions happen. To picture it, imagine two streams of dust, each grain smaller than anything your eyes could ever see, moving almost as fast as light. Now imagine trying to make one grain from one stream hit one grain from the other stream, head-on, in the middle of an enormous underground machine. That is what CERN does. Again and again. When the protons collide, they do not simply break like tiny glass balls. At these energies, matter becomes something more fluid, more strange. The energy of the impact can transform into new particles, some of them heavy, unstable, and short-lived. Particles that do not exist in ordinary life. Particles that vanished from the universe long ago. Particles that appear for less than the blink of an eye, then decay into lighter pieces before they can ever be seen directly. This is why the collider is sometimes described as a time machine. Not because it sends people into the past, but because it recreates, for the tiniest fraction of a second, conditions that once existed when the universe was young. If you travel far enough back in cosmic history, before Earth, before the Sun, before the first stars, before even the first atoms, the universe becomes hotter and denser. Matter had not yet settled into the familiar forms we know. There were no rocks, no oceans, no planets, no solid ground beneath anyone's feet. There was only energy, heat, radiation, a glowing, restless state where the ingredients of matter moved freely before they cooled and locked into place. In the collisions at CERN, scientists can briefly touch that ancient world. Not on the scale of galaxies, not on the scale of stars, but in a microscopic flash, smaller than an atom, gone almost as soon as it appears. For that instant, the collider turns energy into matter, and matter into clues. This is the quiet power of the machine. It does not look into the past by collecting old light from distant stars, the way a telescope does. It looks into the past by rebuilding tiny pieces of the early universe in the laboratory. Each collision is like a spark from the beginning of time. Each detector is built to catch the ashes, and those detectors are among the most extraordinary instruments ever made. They are not cameras in the normal sense. They do not take pictures of particles the way your phone takes a picture of a face, a street, or the night sky. Most particles are far too small, and many live far too briefly. Instead, the detectors watch for trails. A charged particle passes through layers of sensitive equipment and leaves behind little signs of its journey. A tiny flash here, a tiny electrical signal there, a curved path through a magnetic field, a deposit of energy in a block of material. Alone, each sign means almost nothing. Together, they become a map. From that map, scientists can reconstruct what happened in the collision. They can tell which particles were born, which direction they traveled, how much energy they carried, and how they decayed. It is a kind of forensic science. But instead of studying footprints in mud, they study the footprints of particles that lived for less than a trillionth of a second. Around the LHC ring, different detectors have different jobs. Atlas and CMS are the giants. They are enormous, multi-layered instruments, built to search broadly for new particles and rare events. They helped discover the Higgs boson in 2012, the particle linked to the invisible field that gives other particles mass. Alice looks closely at collisions of heavy ions, where matter can melt into an exotic state similar to the hot, dense soup of the early universe. And then there is LHCb, smaller in shape than the biggest detectors, but deeply important to our story. LHCb was designed to study particles containing beauty quarks, also called bottom quarks. These particles are heavy, unstable, and short-lived. They appear in the wreckage of collisions, then quickly fall apart into other particles. That falling apart is called decay. And decay is where secrets hide. Because when a particle decays, it does not do so randomly. The standard model predicts which paths are allowed, how often each path should happen, and what shapes the final spray of particles should make. Most of the time, the predictions work beautifully. The particles appear, they decay. The detectors record the traces. The numbers line up with the rulebook. But every once in a while, physicists find a decay so rare, so delicate, and so cleanly measured that it becomes a perfect place to look for something new. The strange signal at CERN did not come from a huge explosion. It did not come from a new particle standing clearly in the data. It came from one of these delicate decays. A particle was born inside the collider. It lived almost no time at all. Then it died. And in the pattern of its death, something seemed slightly off. That is why the LHC is not just a machine for smashing particles. It is a machine for asking whether reality is exactly what we think it is. Every collision is a question. Every decay is an answer. And sometimes, the answer comes back in a language we do not yet understand. But before we follow that strange particle into its final moment, we need to meet the rulebook that tells it how to die. Because if the particle truly disobeyed the rulebook, even by a little, then the question becomes much larger. Not just what happened at CERN, but whether the deepest map of reality has been missing something all along. Before we can understand why one strange decay matters, we need to understand what it may be disobeying. Physicists often talk about the standard model as if it were a chart. A neat little table of particles, quarks on one side, leptons on another, force carriers in their own quiet row. And somewhere nearby, the Higgs boson, the famous particle connected to the field that gives other particles mass. But the standard model is much more than a chart. It is a rulebook. A set of mathematical instructions describing the smallest known pieces of reality and the ways they are allowed to speak to one another. Every atom in your body is built from particles in this rulebook. The oxygen you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood, everything you can touch, everything you have ever held, everything that has ever formed into a mountain, an ocean, a tree, a planet, or a living body, is made from ingredients that fit inside this invisible structure. At first, that may sound almost disappointing. The universe is so large, so filled with stars, galaxies, storms of gas, black holes, nebulae, and strange worlds orbiting distant suns. And yet, beneath all of it, the menu of known fundamental particles is surprisingly small. A few kinds of quarks, a few kinds of leptons, particles that carry forces, and the Higgs. That is the strange beauty of physics. The universe looks endlessly complicated from far away. But when you move inward, deeper and deeper, past skin, past cells, past molecules, past atoms, past the nucleus, you begin to find a smaller set of rules repeating everywhere. The same particles that build a grain of dust also build a distant moon. The same electrons that move through the screen in front of you also dance around atoms in a star thousands of light years away. The same forces that shape the invisible world beneath your fingertips also operated in the first moments after the Big Bang. That is why the standard model is so powerful. It is not a local rulebook. It is not just true on Earth. As far as we can tell, it works across the visible universe. And for decades, it has passed test after test with almost disturbing precision. Particles predicted by the mathematics were later found in experiments. The W boson, the Z boson, the top quark, and finally, in 2012, the Higgs boson, a particle that had been searched for across generations. When the Higgs was found, it felt like a great door closing. A missing piece had slipped into place. The Standard Model had promised that the piece should exist, and after nearly half a century of searching, the universe quietly said yes. There it is. For many people, that discovery sounded like the end of the story. The rulebook was complete. The final piece had been found. Physics had solved the tiny world. But scientists knew better. Because the Standard Model, for all its success, has a strange problem. It works beautifully, and it is incomplete. It can describe the known particles and several of the fundamental forces with astonishing accuracy. It can predict tiny measurements so well that experiment and theory sometimes agree to more decimal places than seem humanly possible. And yet, when scientists step back and look at the universe as a whole, the rulebook suddenly goes quiet. It does not explain gravity in the same language as the other forces. Gravity, the force holding you to Earth right now, the force shaping planets and stars and galaxies, does not fit neatly inside the Standard Model. It also does not explain dark matter. Something invisible appears to outweigh all the normal matter in galaxies. It bends light. It pulls on stars. It holds galaxies together with gravity. But it does not shine, does not absorb light, and does not appear anywhere in the Standard Model's particle list. The rulebook also does not explain dark energy, the mysterious pressure or property of space that seems to be driving the expansion of the universe faster and faster. And perhaps most haunting of all, the Standard Model does not fully explain why anything made of matter exists at all. In the early universe, matter and antimatter should have been created in nearly equal amounts, and when matter meets antimatter, both vanish into energy. If the universe had followed the simplest version of that balance perfectly, then almost everything should have destroyed itself. No galaxies, no stars, no planets, no oceans, no one listening to this story. And yet, here we are. Matter survived. Somehow, the universe kept a tiny surplus, a small imbalance, a leftover, and that leftover became everything. The Standard Model contains some of the ingredients needed to explain that imbalance, but not enough. The numbers do not seem large enough to account for the universe we actually see. So physicists live with an uncomfortable truth. Their best rulebook is not wrong in the ordinary sense. It is not broken like a bad map. It is more like a map that is extremely accurate wherever it has been drawn, but has blank regions at the edges. And somewhere beyond those edges, something else must be waiting. A new particle, a hidden force, a deeper symmetry, a layer of reality we have not yet reached. This is why CERN matters. The Large Hadron Collider was not built only to confirm what scientists already knew. It was built to push the rulebook into places where it might finally reveal its limits. Because in science, a theory this successful is not easily replaced. You do not throw it away because of one strange result. You test it harder. You measure more carefully. You ask where it works, where it almost works, and where the first tiny difference begins to appear. That is the real meaning of a crack in the Standard Model. It would not mean that everything scientists learned before was useless. It would mean the opposite. It would mean the old rulebook had carried us so far that we had finally reached the place where a larger rulebook begins. This has happened before. Newton's laws described motion and gravity with such power that they changed the world. They could predict the paths of planets, falling objects, tides, and machines. For centuries, they seemed almost final. Then Einstein came along and showed that Newton's laws were part of a deeper picture. Newton was not useless. Newton was still right for ordinary speeds, ordinary distances, ordinary life. But beyond that, near the speed of light, or in the gravity near massive objects, a deeper reality appeared. Something similar may be waiting beneath the Standard Model. Not a destruction of what came before, an expansion, a hidden floor below the floor, a deeper music beneath the music. And that is why physicists pay such close attention to tiny anomalies. A small mismatch in a rare decay can matter more than a dramatic explosion, because the smallest mismatch may point to the exact place where the known theory begins to bend. Most particles at CERN behave exactly as expected. They appear in the collisions. They decay. The detectors record them. The data is compared to the standard model, and the rulebook wins. Again and again. But if you want to find something new, you do not look only at the loudest events. Sometimes you look at the quietest ones, the rarest ones, the decays that happen so infrequently that they become almost like secret messages hidden inside the noise. A common particle decay is like a crowded street. Too much is happening. Too many ordinary effects overlap. A tiny hint of new physics could disappear in the crowd, but a rare decay is different. A rare decay is like a still lake at night. If something unseen touches the surface, even gently, the ripple can be noticed. That is why LHCb studies the delicate depths of particles containing beauty quarks. These particles are heavy enough to be interesting, short-lived enough to reveal the rules quickly, and rare enough in certain decay paths to become sensitive to things too hidden to see directly. A new particle may be far too heavy for the collider to create in the open. It may never appear clearly in the detector. It may never leave a simple signature that says, "Here I am." But in quantum physics, even unseen things can sometimes leave an influence. A hidden particle can briefly affect a process. A hidden force can slightly shift a pattern. A deeper rule can bend the outcome by a tiny amount. Not enough to make the particle behave wildly, just enough to make the numbers lean. And in one rare decay, involving a B meson and a pair of muons, the numbers have been leaning for years. That is where the mystery becomes real. Not in the size of the machine, not in the darkness of the tunnel, not in the fear of what the collider might create, but in the quiet comparison between what the rulebook predicts and what nature actually does. So now we are ready to follow the particle itself. A short-lived particle, born in the violence of a proton collision. A particle carrying a beauty quark. A particle that appears for a vanishing moment, then falls apart. And when it falls apart, the angles of its final pieces seem to whisper that something may be missing. The standard model tells us how this particle should die. CERN watched it die. And the pattern was not quite what the rulebook expected. Inside the Large Hadron Collider, most collisions are ordinary. Not ordinary to us. To us, every collision is almost impossible to imagine. Tiny pieces of matter racing at nearly the speed of light, meeting in the darkness beneath Europe, and exploding into a spray of particles that vanish almost as soon as they appear. But to physicists, most of these events are familiar. They have seen them before. They know what the rulebook predicts. They know which particles are common, which ones are rare, and which paths the debris should follow as it spreads through the detectors. The machine records the traces. The computers sort through the data. The scientists compare the results to the standard model. And most of the time, the universe behaves. The numbers fall into place. The pattern matches. The rulebook survives. But every now and then, inside that enormous ocean of collisions, a rarer event appears. A particle is born that lives for almost no time at all. It carries a heavy ingredient inside it, something physicists call a beauty quark. And because of that beauty quark, the particle becomes especially interesting. The particle is called a B meson. It is not part of ordinary life in any lasting way. It does not sit inside your body like an electron. It does not build the atoms in the chair beneath you or the air around you. It is heavy, unstable, and temporary. It appears in the violent wreckage of a collision. Then, almost immediately, it begins to disappear. In particle physics, disappearing has a more precise name: decay. A particle decay is not death in the way we usually think of death. It is not a body going still. It is not a light fading out. It is transformation. A heavy, unstable particle changes into lighter particles, following rules written into the structure of nature itself. And this is where the Standard Model becomes more than a list. It does not only say what particles exist. It says how they are allowed to change. It tells a B meson which endings are possible. It tells the particle which paths are common, which paths are rare, and which paths should almost never happen at all. Most B mesons decay in ways that are well understood. Their endings may be brief, but they are not surprising. Scientists have watched these patterns for years, counted them, measured them, and compared them to the predictions. But one particular path is different. It is rare, extremely rare, so rare that it is not just another decay, it is a trap for hidden physics. In this rare decay, the B meson transforms into a small group of lighter particles. Among them are two muons. A muon is like a heavier cousin of the electron. It carries the same kind of electric charge, and in many ways it behaves like an electron wearing a heavier coat. But that extra weight makes it important. Muons have appeared again and again in some of the strangest questions in modern particle physics. They are not exotic in the sense of being unknown. Scientists know muons well. Cosmic rays create them high in Earth's atmosphere, and they pass through your body every second without you feeling them. They are ghostly visitors from particle showers above your head, moving through skin, bone, walls, and stone as if the world were almost empty. But inside the rare decay of a B meson, muons become messengers. They carry information about what happened in that tiny moment when the B meson fell apart. And in this story, the problem was not simply that the B meson decayed. It was not even that the decay was rare. The problem was the shape of the decay. When the B meson breaks apart, the final particles do not fly out randomly. They spread in a pattern. They leave the collision point at certain angles with certain relationships to one another. The Standard Model predicts that pattern, not perfectly in every messy detail, because the world of quarks is difficult and turbulent, but carefully enough that scientists know where the final particles should tend to go. Think of it like a firework in the dark. If you knew the exact design of the firework, you could predict the shape it should make when it bursts. A ring, a fountain, a flower, a spray of sparks moving evenly in every direction. Now imagine watching that same firework again and again, thousands of times, millions of times. Each individual burst has some randomness. A spark here, a spark there, tiny differences from one explosion to the next. But after enough fireworks, the average pattern becomes clear. And then, one night, the pattern begins to lean. Not dramatically, not enough for a casual observer to notice, but enough that someone who knows the design looks up and thinks, that is not quite right. That is what happened with this decay. The B meson was not exploding into a visible firework. It was vanishing into particles too small to see. But the detector could reconstruct the trails. The muons curved through the magnetic field. The other particles left their own signatures. And when scientists put the pieces back together, they could measure the geometry of the decay. The angles, the directions, the relationships between the fragments. One of those angular measurements began to stand out. It did not sit where the Standard Model seemed to expect it. At first, that was not enough to cause alarm. Particle physics is full of small mismatches that appear for a while and later disappear. Sometimes the data set is too small. Sometimes the background is not fully understood. Sometimes a statistical fluctuation pretends to be something meaningful. Scientists know this. They are trained to be cautious. So when the first hint appeared, they did not declare that physics had been broken. They did what science demands. They waited. They gathered more data. They refined the analysis. They checked the detector. They compared notes. They asked whether the prediction itself was being calculated correctly. And then they looked again. The strange angle was still there. not perfectly clear, not overwhelming, but present. A soft, persistent difference between what the rulebook predicted and what the particles seemed to do. This is why the mystery became so difficult to dismiss. A one-time anomaly is easy to ignore. A single strange measurement can be a mistake, a fluctuation, a little wave in a noisy sea. But this one did not simply appear and vanish. It returned. Over the years, as more data arrived, the same kind of tension remained. The particle kept dying in a way that seemed slightly bent away from the standard model. And the more scientists looked, the more uncomfortable the question became. Was nature showing us something new? Or were we being fooled by something ordinary that we did not yet understand well enough? This is the delicate place where real science lives. Not in certainty, not in panic, but in tension. The signal was not strong enough to say, this is a discovery, but it was too strong and too persistent to say, this is nothing. That middle ground is where physicists spend years of their lives. They do not chase every strange number. They do not believe every whisper. But when a whisper repeats in the same place, across different analyses, inside a decay that was already known to be sensitive to hidden physics, they begin to listen more carefully. The reason this decay is so powerful is that it may be influenced by particles too heavy for the LHC to create directly. That sounds strange. How can a particle affect an experiment if the machine never actually makes it? But quantum physics is not always as simple as direct appearance. Sometimes, an unseen possibility can briefly affect a process. A particle too heavy to stand in the open may still leave a fingerprint in the way another particle decays. Like a person walking behind a curtain, you never see their face. But you see the fabric move. The rare B-meson decay may be such a curtain. If a new particle exists beyond the standard model, or if a new force touches muons in a subtle way, it might never appear as a bright, unmistakable signal inside the detector. Instead, it might only bend the angles, slightly, quietly, repeatedly, a hidden hand pressing on the pattern. This is why the strange measurement matters. Not because one particle behaved wildly, not because CERN created something dangerous, not because the universe suddenly broke its own laws, but because one of the cleanest windows into hidden physics showed a small distortion, and that distortion did not go away. To understand how strange that is, picture a locked room. Inside the room, a lamp hangs from the ceiling. Every night, the lamp should hang still. No wind, no open windows, no movement. Then one night, you enter the room and notice the lamp swaying. Only a little. You might ignore it. Maybe you bumped the door. Maybe the building shifted. Maybe your eyes are tired. But the next night, the lamp is swaying again. And the next. And the next. Always gently. Always in the same direction. At some point, the small motion becomes harder to dismiss than a large one. Because a large movement could be chaos. But a small, repeated movement suggests a cause. The B-meson decay is that lamp. The standard model says it should hang still. CERN keeps finding that it leans. And somewhere behind that lean may be one of the deepest clues in modern physics. Of course, there is a reason scientists remain careful. This decay is not simple. No decay involving quarks is ever truly simple, because quarks are held together by the strong force, the most intense and complicated of the known forces. The strong force does not behave like an ordinary push or pull. It binds quarks so tightly that they cannot be isolated on their own. It fills the inside of particles with a restless, shifting storm of interactions. That storm makes some predictions difficult. Even when the standard model is correct, calculating exactly what should happen inside a B-meson can be painfully hard. So there are two possibilities. The thrilling one is that a hidden particle or force is tugging on the decay, giving us the first real glimpse of physics beyond the standard model. The quieter one is that the standard model is still right, but our calculation of this particular decay is not yet sharp enough. Both possibilities matter. One would open a new chapter of physics. The other would teach scientists how to calculate the known world more precisely than before. But only one would mean the rulebook has finally begun to crack. For now, the particle's strange death remains suspended between explanation and discovery. A small lean in a rare decay, a bent angle, a repeated whisper from beneath Europe. And the next question becomes unavoidable. How sure are we? Because in particle physics, a strange result is not judged by how exciting it feels. It is judged by how unlikely it is to be a ghost. And to understand that, we need to talk about one of the most important words in all of modern science. Sigma. It is a small word, but in particle physics, it carries enormous weight. It is the difference between a rumor and a result, between a strange coincidence and a possible doorway into a deeper reality, between something scientists can quietly discuss in conference rooms and something they are willing to call a discovery. At first, sigma can sound like cold mathematical language, a word that belongs on a chalkboard, buried in equations, far away from the quiet mystery of a particle dying beneath Europe. But the idea behind it is simple. Sigma asks one question: how surprised should we be? Imagine flipping a coin. If you flip it 10 times and get 6 heads, nothing feels strange. That can happen easily. 7 heads might make you glance at the coin, but you probably would not worry. 8 heads begins to feel unusual. 9 heads feels suspicious. 10 heads in a row makes you stop. Not because 10 heads is impossible. It is possible, but because it is unlikely enough that your mind begins looking for another explanation. Maybe the coin is unfair. Maybe the flips were not random. Maybe something is happening that you did not notice before. Sigma is a scientific way of measuring that feeling. It tells physicists how far a measurement sits from what the rulebook predicted, compared with the normal random wobble that experiments always have. 1 sigma is ordinary. A result 1 sigma away from the prediction can happen all the time. It is the kind of difference that lives inside the natural noise of measurement. 2 sigma is mildly interesting. It is enough to make scientists look twice, but not enough to make them change their view of the universe. 3 sigma is where things begin to feel serious. A 3 sigma result is rare enough that people talk about it. Papers may be written. Conferences may include it. Physicists may begin to wonder whether nature is trying to show them something. But even 3 sigma is not proof. Physics is full of 3 sigma ghosts. Little bumps in the data. Strange patterns that appear for a season. Whispers that vanish when more collisions arrive. And then there is 4 sigma. 4 sigma is much harder to ignore. At 4 sigma, the chance that ordinary randomness created the result is very small. Not impossible, but small enough that experienced scientists begin to lean closer to the screen. This is where the CERN anomaly becomes so compelling. The strange angular pattern in the rare B meson decay has reached a level that can be described as around 4 sigma in certain analyses. That does not mean physics is broken. It does not mean a new particle has been found. It does not mean the standard model has fallen. But it means the mismatch is no longer just a casual oddity. It is a serious tension. A result sitting in the uncomfortable space between maybe and almost. This is one of the hardest places in science. If the signal were weak, scientists could dismiss it. If it were overwhelming, they could celebrate it. But 4 sigma is neither. 4 sigma is the moment when the door is not open, but the handle is moving. To feel what that means, imagine walking past a dark room late at night. You hear a soft sound inside. Once, you might ignore it. A house settles, pipes shift. The wind touches a window. Twice, you might pause. 3 times, you listen. But if the same sound comes again and again, from the same corner of the same room, your mind changes. You still do not know what is there. But you can no longer pretend you heard nothing. That is the position physicists are in. The B meson anomaly is not shouting. It is repeating. And repetition is what makes a whisper powerful. Still, particle physicists are some of the most cautious people in science because they have learned a difficult lesson. The universe is not the only thing that can mislead us. Data can mislead us. Statistics can mislead us. Even excitement can mislead us. When a machine like the Large Hadron Collider studies enormous numbers of collisions, it does not make just one measurement. It makes many, thousands, tens of thousands, different particles, different decay paths, different energy ranges, different angles, different ways to sort the events. And when you look in enough places, something unusual will eventually appear somewhere. Not because nature is hiding a new law there, but because chance has many opportunities to wear a mask. This is sometimes called the look elsewhere problem. Imagine searching a huge field at night with a flashlight. If you shine the beam in one place and see a strange shape, that might be meaningful. But if you sweep the flashlight across thousands of places, sooner or later a shadow will look like something. A face, a figure, a hidden animal. But when you walk closer, it may become only a tree branch, a rock, or the angle of the grass. The more places you search, the more careful you have to be about what you think you have found. Particle physics lives inside this problem. Scientists are not only asking, how strange is this one result? They are also asking, how many chances did we give the data to produce something strange? That is why the standard for discovery is so high. In everyday life, 4 sigma would feel almost conclusive. In medicine, economics, psychology, or ordinary decision-making, a result that unlikely might be treated as extremely strong evidence. But particle physics plays by harsher rules. To officially call something a discovery, scientists usually demand 5 sigma. 5 sigma is not just a little stronger than 4, it is a major leap. It means the probability of the result being a random fluctuation is extraordinarily small. Small enough that the physics community is willing to say, with discipline and confidence, that something real has been seen. That was the level reached when the Higgs boson was announced. Not because scientists wanted to be dramatic, but because they wanted to be sure. A discovery in particle physics is not just a headline. It becomes part of the structure of human knowledge. It enters textbooks. It redirects careers. It shapes future machines. It tells the world that a new piece of reality has been confirmed. So the wall must be high. And the B meson anomaly has not crossed it. Not yet. That is why careful scientists do not say, CERN has discovered new physics. They say something more restrained. They say there is a tension. An anomaly. A persistent deviation. A result that is interesting, maybe even deeply important, but not yet final. This caution may feel frustrating, especially because the story is so tempting. A particle dies the wrong way. The rulebook bends. A hidden force reaches into reality. The first crack in 50 years appears beneath Europe. It sounds like the beginning of a revolution. But science has survived because it refuses to let a beautiful story outrun the evidence. Physicists have been fooled before. More than once, a signal has appeared in particle data that looked exciting, even convincing. The numbers seemed promising. The theories began to multiply. Researchers around the world rushed to explain what the new particle might be. And then more data arrived. The signal shrank. The pattern softened. The bump flattened. The ghost disappeared. Nothing new had been there. Only chance, dressed for a while like discovery. This memory lives quietly behind every modern anomaly. It is why physicists speak carefully. It is why they use words like hint, tension, deviation, and candidate. It is why they do not let themselves celebrate too early. Because in the deepest science, patience is not weakness. Patience is protection. The strange B meson result sits exactly inside that patience. It is strong enough to matter, too weak to crown, persistent enough to keep alive, uncertain enough to remain dangerous. And there is another reason for caution. Even if the result is not random, it may still not be new physics. The measurement could be real, and yet the standard model might still survive. Because sometimes the hardest part of physics is not measuring nature. It is calculating what nature should have done in the first place. The rare decay involves quarks. And quarks live inside a storm. They are bound by the strong force, a force so powerful and complex that it can make simple questions brutally difficult. Even when the underlying rulebook is known, the exact prediction can be clouded by effects that are hard to calculate. This is where the mystery becomes even more subtle. The anomaly could be a message from a deeper layer of reality. Or it could be a reflection of ordinary physics that scientists have not yet computed perfectly. That second possibility is less dramatic. But it is not less important. It is the boring door that must be locked before anyone can walk through the extraordinary one. And until that happens, the signal remains suspended. 4 sigma. Almost, but not enough. A whisper, but not yet a voice. A door handle moving in the dark, but no one has seen what is on the other side. So the question is no longer simply whether the result is strange. It is strange. The question is what kind of strange it is. Is it the strangeness of chance? The strangeness of difficult mathematics? Or the strangeness of something truly new, brushing against the known world from beyond the standard model? To answer that, we need to look at the most dangerous alternative explanation. Not a new particle, not a hidden force, but a messy, ordinary effect inside the calculation itself. A problem with a strangely gentle name, and a very complicated shadow. The charming penguin. The charming penguin. It sounds almost harmless, almost cute. The kind of phrase you might expect in a children's book, not in one of the most difficult questions in modern particle physics. But behind that strange name is a problem serious enough to keep the entire CERN mystery balanced on a knife's edge. Because before scientists can say the rare B meson decay is pointing to new physics, they have to answer a more uncomfortable question. What if nothing new is there? What if the standard model is still right? What if the particle did not really die the wrong way, but our prediction of its death was not sharp enough? This is the quiet danger in the story. The signal may be real, the measurement may be careful, the detector may be working perfectly, the statistics may be strong, and still, the mystery could fade if the theoretical calculation turns out to have hidden uncertainty inside it. In other words, nature may not be wrong. Our math may simply be incomplete. To understand this, return for a moment to the B meson. Inside that short-lived particle is a beauty quark, also known as a bottom quark. This heavy quark is unstable, and when the B meson decays, that quark changes into other particles through a rare process. The decay we are following is rare because it does not happen in the simplest, most direct way. It is not like a ball rolling down a smooth hill. It is more like a whisper passing through a crowded room. Many tiny effects can influence the final pattern. Some are easy to describe, others are not. And in the middle of that difficulty lives the strong force. The strong force is the force that holds quarks together. It binds them inside protons, neutrons, mesons, and other particles. Without it, atomic nuclei would not hold together. Stars would not burn the way they do. Matter would not have the structure we know. But the strong force is also one of the hardest parts of nature to calculate. It does not behave gently. It does not fade in a simple way at short distances. It traps quarks so tightly that they can never be pulled out alone. If you try to separate two quarks, the energy between them grows, almost like stretching an invisible band that refuses to break cleanly. Eventually, the energy becomes strong enough to create new particles instead. The quarks never emerge alone. They remain hidden inside the storm. This storm makes particle decays involving quarks especially difficult. The Standard Model may tell scientists the underlying rules, but turning those rules into one exact prediction can be brutally hard. It is a little like knowing all the rules of weather and still struggling to predict the path of one tiny swirl inside a thunderstorm. The laws are known, the system is real, but the motion is complicated. In the rare B meson decay, scientists try to isolate measurements that are cleaner, more stable, and less vulnerable to this storm. That is why the angular observables matter so much. They were designed to reduce some of the messy theoretical uncertainty and make the decay a sharper test of the Standard Model. But reduced uncertainty is not the same as no uncertainty. Some shadows remain. One of those shadows involves another quark, the charm quark. The charm quark is lighter than the beauty quark, but still much heavier than the quarks inside ordinary protons and neutrons. It can appear briefly inside the complicated quantum process that leads to the B meson's decay, not as a simple final particle flying out into the detector, not as something scientists can point to directly in the wreckage, but as a temporary influence, a flicker in the middle of the process, a loop, a hidden detour. And because this charm quark effect can disturb the same kind of decay that already carries the nickname penguin, physicists gave the problem a strange name, the charming penguin. The name may be playful. The problem is not. If the charm quark's hidden influence is larger than expected, it could shift the angular pattern of the decay. It could move the measurement away from the clean Standard Model prediction without requiring any new particle, any new force, or any deeper layer of reality. The anomaly could still be there, but the explanation would be ordinary, not simple. But ordinary, known physics, wearing a mask. This is why scientists cannot rush. The most exciting answer is not always the right one. A new force would be thrilling. A new particle would be historic. A crack in the Standard Model would reshape the future of physics. But before physicists are allowed to believe in those possibilities, they have to make sure the charming penguin is not large enough to explain the signal by itself. And that is difficult. Because calculating these charm effects is not like measuring the length of a table or the weight of a stone. It is more like trying to hear one quiet note inside an orchestra while standing outside the concert hall. The note is there. The music is real. But the sound reaches you blurred, mixed, and softened by everything around it. Scientists build mathematical tools to separate the note. They compare different decay channels. They use independent measurements. They test models. They search for patterns that would reveal whether charm effects are responsible. And the situation remains tense. Many analyses suggest that the charm contribution may not be large enough to explain the whole anomaly. That is what keeps the possibility of new physics alive. But the calculation is difficult enough that the door cannot be fully closed. Not yet. So the rare decay sits between two worlds. In one world, the charming penguin is only a small smudge. It cannot explain the bent angle. The Standard Model prediction remains too far away from the measurement, and something new must be quietly touching the process. In the other world, the charming penguin is larger than expected. The smudge spreads. The prediction shifts. The anomaly loses its power, and the Standard Model survives again, not because the signal was fake, but because the ordinary physics was more complicated than anyone realized. Both worlds are possible, and this is what makes the CERN mystery so fascinating. It is not a simple battle between truth and error. It is not a story where brave scientists discover something strange and stubborn skeptics refuse to believe them. Real science is more careful than that. The scientists themselves are both brave and skeptical. They want the anomaly to be real, because a true crack in the Standard Model would open a new era. But they also know that wanting something is dangerous. The universe does not reward excitement. It rewards patience. So they ask the same questions again and again. Can the detector be trusted? Can the background be modeled? Can the statistical significance survive? Can another experiment see the same pattern? Can the theory prediction be sharpened? Can the charm effects be controlled? Only when enough of these questions are answered does a mystery become a discovery. Until then, the strange decay remains suspended in the dark. A particle died. Its fragments flew outward. The muons carried their message through the detector. The angles were measured. The result leaned away from the rulebook. And now physicists must decide whether that lean came from a hidden piece of the universe, or from the known universe being harder to calculate than expected. There is something beautiful about that uncertainty. It reminds us that science is not only the search for dramatic answers, it is the discipline of refusing easy ones. A less careful world would already have declared victory. A less careful story would say that CERN has broken physics, that a new force has been found, that the standard model has finally collapsed. But the real story is quieter and more powerful. A number is leaning. The rulebook is trembling. The explanation is not yet known. And somewhere between the charming penguin and the possibility of new physics, the future of the mystery is waiting. But this is not the only place where the standard model seems incomplete. There is another mystery, older and larger, written not in the death of one particle, but in the survival of everything. Because long before CERN was built, long before Earth formed, long before the first stars lit the dark, the universe faced a problem. Matter and antimatter should have destroyed each other. The cosmos should have emptied itself into light. And yet, matter survived. The stars exist. The planets exist. You exist. So if the strange decay at CERN is a whisper from beyond the known rulebook, the matter-antimatter mystery is a much older question, one written into every atom of your body. Before there was Earth, before there were oceans, before the first mountains rose or the first clouds moved across a blue sky, there was a question hidden inside the birth of the universe. Why did anything survive? Not why did stars form? Not why did planets cool? Not why did life begin? But something even deeper. Why was there matter left over at all? It sounds like a strange question, because matter feels so obvious to us. You are made of matter. The room around you is made of matter. The air moving through your lungs, the water in the oceans, the dust on the moon, the iron in Earth's core, the burning gas inside the sun, all of it is matter. Matter is the ordinary stuff of existence. It is so familiar that we rarely stop to ask why it is here. But physics does ask. And when physics asks honestly, the answer becomes unsettling. In the beginning, the universe should not have favored matter. As far as scientists understand, the early universe should have created matter and antimatter together. For every particle, an opposite partner. For every electron, a positron. For every proton, an antiproton. For every piece of ordinary stuff, a mirror version with the opposite charge. Matter and antimatter are not enemies in the emotional sense. They are opposites in the physical sense. And when they meet, they do something extraordinary. They annihilate. A particle touches its antimatter twin, and both vanish. Their mass turns into energy, not partly, not inefficiently, but almost perfectly. Matter becomes light. Substance becomes flash. Two opposite pieces of reality erase each other and leave behind radiation. Now imagine the young universe filled with equal amounts of both, matter and antimatter, born together, crowded together, rushing through a hot and violent cosmic fog. If the balance had been perfect, the ending seems unavoidable. Matter would meet antimatter. Particle would meet mirror particle. Again and again, across the newborn universe, they would annihilate. And after enough time, almost nothing solid would remain. No atoms, no stars, no galaxies, no Earth. No one to wonder what happened. Only light, spreading through an empty cosmos. That is the universe we might have expected. But it is not the universe we have. The universe we have is filled with matter. Galaxies are made of matter. Stars are made of matter. Planets are made of matter. Your body is made of matter. Somehow, in the ancient battle between matter and antimatter, matter won. Not by much. It did not need to win by much. The imbalance may have been incredibly small. A tiny tilt in the cosmic scale. For every enormous number of matter and antimatter particles that destroyed each other, perhaps only one extra particle of matter survived. But those leftovers became everything. Every atom in your hand. Every grain of sand on every beach. Every mountain range. Every comet. Every world. Every living cell. All of it may be made from the small remainder of a universe that almost erased itself. This is one of the most beautiful and disturbing ideas in modern physics. You are not made from the main event. You are made from what survived after the main event was nearly over. You are a leftover, a rare survivor from the first great cancellation. And that raises the question that still haunts physics. What gave matter the advantage? Why was the mirror not perfect? If matter and antimatter were truly equal in every way, then matter should not have won. The universe should have balanced itself into emptiness. So somewhere, somehow, the mirror had to crack. There had to be a difference. A tiny one. A flaw in the symmetry. A place where matter and antimatter do not behave exactly the same. Scientists call this CP violation. The name is technical, but the idea can be felt without equations. C stands for charge. It asks what happens if every particle is replaced with its opposite charge, turning matter into antimatter. P stands for parity. It asks what happens if the universe is reflected like a mirror, left and right exchanged. For a long time, physicists wondered whether nature would look the same under these transformations. Would the laws of physics remain unchanged if matter became antimatter and the world were reflected? In a perfectly symmetrical universe, the answer would be yes. Matter and antimatter would be perfect mirror images. Every process involving matter would have an antimatter version happening in exactly the same way. Same rates. Same patterns. Same behavior. The mirror would be flawless. But the real universe is not flawless. The weak force, one of the fundamental forces of nature, does not treat all mirrors perfectly. In certain particle decays, matter and antimatter behave just a little differently. Not enough to notice in daily life. Not enough to change the way a rock falls or the way a flame burns. But deep inside the tiny world, the difference is real. A particle may decay one way slightly more often than its antimatter twin. A pattern may lean one direction instead of balancing perfectly. A number may refuse to match its mirror. That is CP violation, the cracked mirror. And it matters because without some crack like this, the universe has no obvious way to become matter-dominated. The cosmos needed a preference, a tiny unfairness. A hidden rule that said matter and antimatter are almost the same, but not quite. CERN has spent years studying that difference, and the LHCb experiment is especially suited for this task. Because LHCb studies particles containing beauty quarks, and these particles often decay in ways that reveal tiny asymmetries between matter and antimatter. The same machine that watches rare B meson decays for possible signs of new physics also watches matter and antimatter versions of particles fall apart, comparing them with extreme precision. Imagine two dancers. One is matter. The other is antimatter. If the mirror were perfect, every step one dancer makes would be copied exactly by the other. Same rhythm, same turn, same angle, same ending. But if one dancer hesitates slightly, or turns a little faster, or chooses one path just a little more often, the mirror has failed. That failure is not a mistake. It is information. It is the universe revealing that symmetry is not absolute. For decades, scientists observed CP violation in certain particles called mesons, which are made of a quark and an antiquark. Those discoveries were important. They showed that nature really can treat matter and antimatter differently. But there was still a deeper question. Could this cracked mirror be seen in baryons? Baryons are particles made of three quarks. Protons and neutrons are baryons, and protons and neutrons build the nuclei of atoms. So when scientists ask whether CP violation exists in baryons, they are asking whether this asymmetry reaches into the same broad family of matter that makes up the visible world around us. For a long time, the answer was uncertain. Hints appeared. Evidence grew. But certainty is hard in particle physics. Then, LHCb found a new piece of the puzzle. By studying a heavy baryon and comparing its decay with the decay of its antimatter partner, scientists observed that the two did not behave in perfectly mirrored ways. The matter version and the antimatter version decayed with a measurable difference. The mirror cracked in a new place. This was not the final answer to why the universe exists. It did not solve the matter-antimatter mystery. But it was a real step. A new kind of asymmetry seen in the family of particles that includes the building blocks of ordinary atomic matter. And yet, as always, the universe gave with one hand and held back with the other. Because even though CP violation is real, even though the mirror is cracked, the cracks we have measured so far are too small. They are not enough to explain the great survival of matter. The standard model allows some CP violation. It predicts certain asymmetries. It has enough room for a cracked mirror, but not a cracked mirror wide enough to explain the universe we see. That is the problem. The known asymmetries are real, but they do not seem powerful enough to leave behind all the matter in the cosmos. So the matter-antimatter mystery remains open. Scientists have caught the universe playing favorites, but not strongly enough. They have seen matter and antimatter behave differently, but not differently enough. Somewhere, there may be another source of CP violation, another hidden process, another place where the mirror breaks more deeply than the standard model currently allows. And that possibility brings us back to the strange signal beneath Europe. Because if the rare B meson decay is truly being touched by new physics, then it may not be an isolated oddity. It may belong to a larger pattern, a pattern of missing explanations, dark matter. The matter-antimatter imbalance, the absence of gravity from the standard model, the strange behavior of certain muon-related measurements, the persistent tension in rare beauty particle decays. Each mystery is different. Each has its own data, its own difficulty, its own careful language. But together, they suggest the same uncomfortable truth. The standard model is brilliant, but it is not the final story. It is a lantern in a vast dark room. The lantern is bright. It shows us a great deal, but beyond the circle of light, the room continues. The matter-antimatter mystery may be one of the clearest signs that something beyond the lantern is waiting. Because the universe itself is evidence. The stars are evidence. The galaxies are evidence. Your own body is evidence. Every atom says the same thing. Matter survived. And no complete explanation has yet been found. There is a quiet wonder in that. You can look at your hand and see skin, veins, lines, fingerprints. But beneath that ordinary image is a cosmic fact. Your hand exists because the early universe was not perfectly balanced. Some ancient symmetry failed. Some tiny preference, hidden in the laws of nature, allowed matter to remain after antimatter nearly erased it. The same mystery is written in a sleeping child, in the dust of Mars, in the rings of Saturn, in the oldest stars, in the atoms of every world. CERN cannot answer all of this at once. No single experiment can. But CERN can study the cracks, one decay at a time, one asymmetry at a time, one strange measurement at a time. It can ask whether particles and antiparticles truly mirror each other. It can ask whether rare decays hide new influences. It can ask whether the muon, the beauty quark, or the charm quark are pointing toward something deeper. And it can keep testing the rulebook until the missing pages begin to show. This is why the story of the B-meson anomaly matters more after we understand antimatter. It is not just a technical mismatch. It sits inside a larger landscape of things the standard model cannot fully explain. The particle that died the wrong way may not be the key to the matter-antimatter mystery, but it lives in the same world of questions. A world where tiny differences can decide whether a universe becomes empty light or a place filled with stars. And now, after the cracked mirror of matter and antimatter, we come to another strange question. If antimatter is the opposite of matter in so many ways, does it fall the same way? If you could hold a single atom of antimatter in empty space, release it gently, and watch it move, would it fall down like everything else? Or would it rise? For nearly a century, that question sounded almost impossible to answer, because antimatter destroys itself the instant it touches ordinary matter. You cannot put it in a jar. You cannot rest it on a table. You cannot hold it in your hand. To study it, scientists had to build a bottle with no walls, a trap made not of glass or metal, but of invisible force. To hold antimatter, scientists had to do something that sounds impossible. They had to build a bottle that antimatter could never touch. A normal bottle would not work. Glass is made of matter. Metal is made of matter. Plastic, stone, air, dust, even the smallest speck on the wall of a container, all of it is matter. And antimatter cannot safely touch matter. The moment an antimatter particle meets its ordinary twin, both vanish in a burst of energy. So if you tried to place antimatter inside a normal container, the container itself would destroy it. The walls would not protect the antimatter. The walls would be the danger. So at CERN, scientists use something stranger. They use fields, invisible forces, magnetic and electric traps designed to hold charged antimatter particles in empty space without letting them touch anything solid. A bottle with no glass, a cage with no bars, a place where the prize floats in the middle, held by force alone. This is the world of the antimatter experiments at CERN. Here, scientists do not work with large amounts of antimatter. They do not create glowing tanks of it, or powerful fuel cells, or anything like the science fiction stories imagine. They work with tiny numbers of particles. A few antiprotons, a few positrons. Then, with extraordinary care, they combine them into antihydrogen, the antimatter version of the simplest atom in the universe. Ordinary hydrogen is made from one proton and one electron. Antihydrogen is made from one antiproton and one positron. It is hydrogen, reflected in the mirror. And because hydrogen is so simple, antihydrogen is one of the best ways to ask whether matter and antimatter are truly perfect opposites. Do they absorb and emit light in the same way? Do they respond to forces in the same way? Do they behave like perfect mirror twins? Or is there, somewhere in the details, a tiny difference that could help explain why antimatter almost disappeared from the universe? For years, scientists compared antihydrogen with ordinary hydrogen as carefully as they could. And again, the mirror looked almost perfect. Antimatter seemed to obey the same rules as matter. That was beautiful. And frustrating, because the universe itself says the mirror cannot be the whole story. If matter and antimatter were perfectly equal in every meaningful way, then the ancient universe should have erased almost everything. Yet matter survived. So scientists kept asking new questions. And one of the simplest questions was also one of the hardest to answer. If you let go of antimatter, Which way does it fall? For ordinary matter, the answer is so familiar that we almost stop noticing it. A phone falls down. A stone falls down. Rain falls down. Dust settles down. Your body rests on the ground because Earth is pulling it downward. Gravity feels like the most ordinary rule in the world. But antimatter is the mirror of matter. Its charge is reversed. Its identity is reversed. So for decades, physicists asked a strange and honest question. Could its gravity be reversed too? Could antimatter fall upward? Could it respond to Earth in the opposite way? This was not a fantasy question. It was a real scientific question, because no one had directly watched neutral antimatter fall before. The problem was not imagination. The problem was control. Gravity is extremely weak compared with the forces used to trap antimatter. A small magnetic effect can easily overpower the gentle pull of the entire Earth. So to watch antihydrogen fall, scientists had to create it, cool it, hold it, and then release it so gently that gravity could finally show its influence. They built vertical traps. They held antihydrogen atoms inside magnetic fields. Then they slowly weakened the trap. And they watched where the atoms went when they escaped. If antimatter fell upward, more atoms would leave toward the top. If antimatter fell downward, more would leave toward the bottom. The result was quiet, but profound. Antimatter fell down. Not perfectly measured in every tiny detail, not the final word on every possible gravitational question, but clear enough to close one of the strangest doors in physics. Antihydrogen, the mirror atom, moved downward under gravity. The same direction as ordinary hydrogen, the same direction as a falling leaf, a dropped coin, a sleeping body resting on Earth. There was no simple anti-gravity, no upward fall, no easy answer to the missing antimatter problem. The universe had not lost its antimatter because antimatter floated away. That possibility faded, and the mystery remained. This is how CERN often works. It does not always solve a question by opening a door. Sometimes it solves a question by closing one. A beautiful idea is tested. Nature answers. And the map becomes a little clearer. Antimatter falls down. So the question of why matter survived must be answered somewhere else. In another asymmetry, another hidden process, another crack in the mirror. But antimatter is not the only ghost CERN studies. There are other particles even more elusive, particles that pass through us constantly. Particles so light, so quiet, and so unwilling to interact that they can cross entire planets, almost as if the planets were empty space. They are called neutrinos, and right now, as you listen, they are passing through your body. Not one, not a few, trillions. Every second, enormous numbers of neutrinos stream outward from the sun and other cosmic sources. They pass through Earth in daylight and darkness, through oceans, mountains, buildings, and living bodies. You do not feel them because they almost never touch anything. To a neutrino, the solid world is nearly transparent. A wall is mostly empty. A mountain is mostly empty. Even the Earth itself is mostly empty. That is not how the world feels to us. To us, stone is solid, metal is hard, and the ground beneath us is firm. But at the scale of particles, matter is mostly space, and neutrinos are among the best travelers through that space. They carry no electric charge. They interact only through gravity and the weak force, and because the weak force acts over extremely tiny distances, a neutrino can pass through enormous amounts of matter without leaving a trace. This makes neutrinos extremely hard to detect. To catch one, scientists often build huge detectors deep underground, far from surface noise, filled with tons of material, waiting for the rare moment when a neutrino finally bumps into something. Most pass through, a few interact, and from those few, scientists learn. For a long time, the Large Hadron Collider was not thought of as a neutrino machine. The collisions surely created neutrinos, But those neutrinos escaped invisibly. They slipped away down the beamline, through rock, through concrete, through the earth, carrying information no detector was catching. Then, scientists placed new detectors in just the right places. Small compared with the great giants like Atlas and CMS, but positioned carefully, like nets placed in a hidden current. And for the first time, neutrinos created inside a particle collider were caught. Ghosts from the collisions. Particles born in the violence beneath Europe, finally leaving signatures inside a detector, built to wait for them. This opened a new kind of window. Not a window into stars, not a window into distant galaxies, but a window into ghost particles made by human-built collisions, at energies that can teach scientists new things about how neutrinos behave. And neutrinos matter because they, too, are connected to the unfinished story of the universe. They have mass, but unbelievably little. They come in different types or flavors, and as they travel, they can change from one type into another, as if shifting identity in flight. This strange behavior already tells physicists that the standard model, in its simplest original form, was not complete. Neutrinos force the rulebook to stretch, and some scientists suspect that neutrinos may be tied, in ways not yet fully understood, to the great matter-antimatter imbalance. Perhaps somewhere in the ghostly behavior of neutrinos, the early universe found part of its preference for matter. Perhaps not. The answer is still hidden. But that is the pattern again. At CERN, scientists study the visible by measuring tracks. They study the invisible by measuring what is missing. A particle that leaves no mark can still reveal itself if energy seems to vanish. A ghost can still be known by the shape of the silence it leaves behind. This is also how scientists search for dark matter at colliders. Dark matter, if it is made of particles, may pass through detectors without interacting. It may not flash, curve, or deposit energy in the ordinary way. So researchers look for imbalance. They measure what comes in. They measure what comes out. And if something seems to carry energy away without being seen, that missing energy could be a clue. So far, dark matter has not appeared clearly at CERN. The invisible majority of the universe remains invisible. But the search itself is meaningful. Because every non-detection narrows the possibilities. Every silent result tells scientists where dark matter is not hiding, or how weakly it must interact, or how different it may be from the simple particles we first imagined. This is the quiet patience of modern physics. Antimatter is made and dropped. Neutrinos are caught after passing almost untouched through the world. Dark matter is searched for in the gaps. Rare decays are measured by their angles. Again and again, CERN asks the same kind of question in different forms. What is visible? What is missing? What behaves as expected? What leans away? And somewhere among these questions, the strange B meson signal still waits. It is not alone. It belongs to a larger landscape of mysteries, where matter survived when it should have vanished, where antimatter falls like ordinary matter, but remains almost absent from the universe, where ghost particles pass through us, and where dark matter shapes galaxies without showing itself. The world we see is only the surface. Below it is a deeper world of tracks, decays, asymmetries, missing energy, and tiny patterns that may point beyond the known map. And to read those patterns, CERN must handle something almost as overwhelming as the physics itself. Data. An ocean of it. Every collision, every detector signal, every possible trace of a particle's path adds to a flood too large for any ordinary machine to hold. So before we can understand what happens next, we need to look at the hidden brain behind the collider, the global system that sorts the noise from the signal, the invisible network that may already hold the answer to the strange measurement beneath Europe. Because the truth may not be waiting in a future collision. It may already have happened. It may already be recorded. It may be sitting silently in the data, waiting for scientists to finish reading it. The Large Hadron Collider does not only create collisions, it creates memory. Every time particles meet beneath Europe, the detectors are listening. Layer after layer of electronics waits for the faint signs of something passing through. A charged particle leaves a trail. A photon deposits energy. A muon slips through deeper layers. A jet of particles sprays outward like a tiny storm blooming from a point smaller than an atom. For one collision, the information may seem manageable. A few tracks. A few energy deposits. A few traces in the detector. But the LHC does not produce one collision. It produces them in floods. Again and again, bunches of protons cross inside the detectors, and the machine must decide almost instantly which moments matter and which moments can be forgotten. This is one of the strangest truths about CERN. The machine creates far more information than it can keep. If scientists tried to save every possible collision in full detail, the data would overwhelm the storage systems almost immediately. The detectors would not become a library of the universe. They would drown in their own memory. So CERN had to solve a problem that sounds almost impossible. How do you recognize a discovery before you know what it looks like? How do you decide, in a tiny fraction of a second, which collision might contain a clue to new physics? How do you throw away almost everything without throwing away the one event that matters? This is the job of the trigger system. A trigger is not a trigger in the sense of firing a weapon. It is a decision, a lightning-fast judgment made by electronics and algorithms deep inside the machinery of the experiment. Most collisions are ordinary. They may still be beautiful. They may still be complex. They may still involve particles appearing and vanishing in ways that would seem miraculous to anyone watching from outside the field. But to the experiment, they are familiar. They match known patterns. They do not contain the rare shapes scientists are looking for, so they are discarded. Not because they are meaningless in a philosophical sense, but because the machine cannot keep everything. To find the extraordinary, the collider must let go of the ordinary. There is something almost haunting about that. Beneath Europe, countless collisions happen and vanish forever. Tiny recreations of extreme physics appear for an instant, are judged by invisible systems, and then disappear without being saved. Only a small fraction survives. Only the events that seem interesting enough, strange enough, energetic enough, or useful enough are allowed into the deeper memory of the experiment. Those events become data, and the data begins its second life. It leaves the detector and enters a much larger system, the computing world behind CERN. This hidden side of modern physics is easy to overlook. When people imagine particle physics, they picture the tunnel, the magnets, the collisions, the giant detectors, and perhaps the famous control rooms filled with screens. But behind every discovery is another machine. Not a circular tunnel underground, not a magnet colder than space, but a planet-wide brain. The data from CERN does not sit quietly in one computer. It is distributed, copied, processed, shared, sent across networks to research centers around the world. Thousands of scientists in different countries can work with pieces of the same enormous puzzle. A collision recorded in Europe may be analyzed by a researcher in the United States, compared with simulations produced elsewhere, checked by teams on another continent, and later folded back into a global understanding of the experiment. Particle physics is no longer the work of one room. It is the work of a world, and it has to be. Because the signals are too rare, the calculations too heavy, and the data too vast for one place to handle alone. Remember the strange meson decay. The mystery did not appear after watching a handful of particles. It emerged only after scientists gathered enormous numbers of events, searched through them carefully, identified rare decay patterns, removed backgrounds, checked detector effects, and compared the final measurements with difficult theoretical predictions. A single rare decay can be like a whisper. To hear it clearly, scientists need silence. But there is no silence inside the LHC. There is only noise. So they build silence out of statistics. They collect enough events that the random noise begins to smooth out. They compare enough patterns that the signal can rise. They test enough alternatives that ordinary explanations begin to shrink. This is why more data matters. If the strange B meson anomaly is only a fluctuation, then more data should weaken it. The pattern should soften. The measurement should drift back toward the standard model. The whisper should fade into the background, the way many ghosts in particle physics have faded before. But if the anomaly is real, more data may do the opposite. The pattern may sharpen. The tension may grow. The strange angle may remain tilted, not just in one batch of collisions, but in another, and another, and another. That is what makes this moment so powerful. The answer may not require a new tunnel. It may not require a new machine. It may not even require a future collision. Some of the evidence may already exist, recorded, stored, waiting. Somewhere inside the vast archives of particle data, there may already be enough information to know whether the strange signal is a doorway or a mirage. The universe may have already given its answer. Human beings are still learning how to read it. Think about that for a moment. The truth might be fixed already. In the data, the particle has already died. The muons have already flown outward. The angles have already been written into the detector. The computers have already captured the traces. The mystery is not waiting for nature to decide. Nature has decided. The uncertainty belongs to us. We have the cards in our hand, but we have not finished turning them over. This is one of the quietest forms of suspense in science. There is no countdown clock, no explosion, no dramatic announcement echoing through a control room. Only teams of scientists working through oceans of data, improving calibrations, checking assumptions, comparing simulations, testing backgrounds, refining selections, and asking again and again whether the signal survives. Science at this level is not fast. It is not simple. It is not one person looking at a graph and shouting that the universe has changed. It is months and years of careful work. A result must be cleaned, then checked, then challenged, then checked again. Every possible ordinary explanation must be given a fair chance. The detector must be understood. The trigger must be understood. The reconstruction must be understood. The background processes must be understood. The theory prediction must be understood. Only then can a strange number begin to mean something. This patience may seem slow from the outside, but it is the reason science can be trusted. A rushed answer is easier. A careful answer is stronger. And in the case of the B meson anomaly, care matters more than excitement, because the stakes are enormous. If the signal fades, it will join the long history of almost discoveries, beautiful hints that taught scientists something, even though they did not reveal new physics. If the signal grows, it may become one of the most important clues in modern particle physics. A sign that something outside the standard model is affecting rare decays. A sign that muons may be part of a deeper pattern. A sign that the known rulebook, as powerful as it is not complete. This is why the data feels alive. Not alive like an organism. Alive like a dark ocean at night. Most of it looks calm from a distance. But beneath the surface, there may be movement. A rare event. A faint asymmetry. A hidden pattern. A small angle leaning away from expectation. And the only way to find it is to keep looking. CERN has also begun to change the way it listens. As the data grows, the old methods are no longer enough. Experiments are improving their triggers, using faster electronics, more powerful computing, and increasingly sophisticated algorithms to recognize interesting events in real time. The goal is not simply to collect more. The goal is to collect more wisely. Because a future discovery may not look like the discoveries of the past. It may not appear as a clean new particle peak rising from a graph. It may appear as a subtle distortion across many measurements, a pattern distributed through rare decays, a mismatch between electrons and muons, a missing energy signature, a tiny imbalance that only becomes visible when many clues are placed together. The deeper physics may not shout. It may hum. And to hear a hum, the machine must become a better listener. That is what the next era of CERN is about. Not only higher collision rates, not only larger data sets, but sharper attention. The ability to recognize what is unusual before it is lost. The ability to preserve strange events without already knowing why they are strange. The ability to search not only for the particles scientists expect, but for the patterns they have not yet imagined. This matters because the universe has surprised us before. It rarely announces its secrets in the way people predict. The Higgs boson was expected, but it still required decades of searching. Neutrino masses were not part of the simplest standard model, yet nature revealed them. Matter-antimatter asymmetries appeared in places scientists had to measure with extraordinary care. Exotic particles emerged from quark combinations once considered uncertain or rare. Again and again, the universe has shown that reality is richer than our first maps. The question now is whether the strange B meson signal belongs to that tradition. Is it another path into a deeper world? Or is it a shadow cast by ordinary physics? The next data may decide, and the answer, whatever it is, will matter. Because if the signal disappears, scientists will learn something essential about the limits of their calculations, the behavior of rare decays, and the danger of being fooled by patterns too early. But if the signal remains, if it grows stronger, if it moves from 4 sigma toward the sacred 5, then the story changes. The whisper becomes a voice. The leaning number becomes a discovery. The small crack becomes an opening. And the standard model, the most successful rulebook in the history of particle physics, would no longer be merely incomplete in the abstract. It would be incomplete in the data. That is different. Everyone already knows the standard model cannot explain everything. It cannot explain dark matter. It cannot fully explain the matter-antimatter imbalance. It does not include gravity in the same framework as the other forces. But those are large cosmic mysteries. They tell us the rulebook is missing something somewhere. A confirmed anomaly in a rare particle decay would be more direct. It would point to a location, a place to dig, a specific process where the known equations fail. That is why physicists care so much about small deviations. A great mystery tells you that something is missing. A precise anomaly tells you where to look. And so, under the surface of all the caution, there is real anticipation. Not panic, not certainty, but anticipation. The feeling that somewhere in the data, the next chapter may already be waiting. Maybe the charming penguin will explain the anomaly. Maybe the signal will fade. Maybe the standard model will hold again, strong and brilliant as ever. Or maybe, hidden among trillions of traces, there is a pattern that will not go away. A pattern that says the muon knows something. A pattern that says the beauty quark is pointing somewhere. A pattern that says the universe has another layer, just below the one we have mapped. The machine beneath Europe keeps listening. The detectors keep recording. The computers keep sorting. The scientists keep asking the same patient question. Does the strange number survive? And until the answer is clear, the mystery remains suspended in the dark. Not solved, not dismissed, waiting, like a signal beneath deep water, like a message half buried in static, like a door in the rulebook, still closed, but no longer perfectly still. And now we come to the final question. What happens if the door opens? What happens if the anomaly survives every test? What happens if the standard model, after 50 years of victory, finally shows a confirmed crack? The answer would not simply belong to CERN. It would belong to the entire human story. Because when the deepest rulebook breaks, even slightly, It means reality is larger than we knew. If the strange signal survives, physics will not end. The universe will not collapse. The old rulebook will not be thrown away like a broken machine. That is not how science works. When a great theory finally shows a limit, it does not always die. Sometimes, it becomes part of something larger. Newton's laws did not vanish when Einstein revealed a deeper picture of gravity. They remained true in the world where they had always worked: slow speeds, ordinary distances, everyday motion. They became a chapter inside a bigger book. The Standard Model may be waiting for the same fate. For 50 years, it has described the particle world with astonishing success. It has predicted, explained, and survived. It has guided scientists through the invisible architecture beneath matter itself. But if the B-meson anomaly becomes real, if the strange angle remains, if the signal grows beyond doubt, then physicists may finally have something they have wanted for decades. Not just a suspicion that the Standard Model is incomplete. They already have that. Dark matter tells them that. Gravity tells them that. The matter-antimatter mystery tells them that. They would have something more precise. A place where the rulebook bends. A location on the map where the known equations do not quite meet the world. That would be priceless. Because a mystery like dark matter is enormous. It tells us that something is missing, but not exactly where to dig. A confirmed anomaly in a rare particle decay is different. It is a clue with coordinates. It says, look here. Look at beauty quarks. Look at muons. Look at rare decays. Look at the quiet places where new physics may touch the known world without showing itself directly. If the signal is real, scientists would begin asking what kind of hidden thing could create it. Maybe a new particle. One too heavy for the current collider to produce openly, but still able to leave a faint influence inside a rare decay. Maybe a new force. A fifth interaction of nature, subtle and selective, touching some particles more than others. Maybe something even stranger. A hidden symmetry. A new field. A deeper structure underneath the particles we already know. At first, the answer would not be clear. A real crack does not immediately reveal the whole continent beyond it. It only proves that the wall is not solid. But that would be enough to change the direction of physics. Theorists would build new models. Experimentalists would design new searches. Old data would be checked again. New data would become even more valuable. Other decays would be studied for matching patterns. Electrons and muons would be compared with greater care. The LHCb experiment would become even more central to the story, because it listens exactly where the whisper was heard. Atlas and CMS would look for related clues in their own enormous detectors. Other experiments around the world would join the hunt. Science would not move as one person's sudden revelation. It would move like a tide. Slowly at first, then with growing force. If the anomaly survives, it may become the first confirmed opening into physics beyond the Standard Model. And if that happens, the consequences could reach far beyond one particle decay. It might help explain why matter survived. It might point toward the nature of dark matter. It might reveal why the muon seems to appear so often near the edge of modern physics. It might show that the families of particles are not as equal as scientists once thought. Or it might open questions no one has yet imagined. That is the strange thing about real discovery. The answer you find is rarely the final answer. It is usually a better question. The discovery of the electron did not end physics. It opened the atomic world. The discovery of the atomic nucleus did not end physics. It opened nuclear science. The discovery of the Higgs boson did not end physics. It confirmed one great piece of the Standard Model, and then made the missing pieces even more obvious. So if the CERN signal becomes real, it will not be the end of the story. It will be the beginning of a new one. But we must also hold the other possibility. The signal may fade. More data may soften the tension. The angles may drift back toward the Standard Model. The charming penguin may turn out to be larger than expected. The calculation may improve, the uncertainty may shift, and the strange death of the bee meson may become ordinary again. If that happens, it will feel disappointing. But it will not be a failure. It will be science doing what science is meant to do. Testing, doubting, correcting, refusing to worship a beautiful idea before nature has approved it. The history of physics is filled with ghosts, signals that seemed promising, bumps that looked meaningful, hints that pulled the attention of brilliant minds, only to vanish when the data grew clearer. Those ghosts were not useless. They taught scientists how to be more careful. They sharpened methods. They improved detectors. They forced better calculations. They reminded the human mind that wanting a revolution is not the same as finding one. So even if the anomaly disappears, something will still be gained. The rare decay will be better understood. The standard model will have survived another difficult test. The map will be stronger where it once looked weak. And the search will continue, because the deeper mysteries will still remain. Dark matter will still hold galaxies together invisibly. Gravity will still stand apart from the standard model. Neutrinos will still pass through us, like quiet messengers from another layer of reality. Matter will still exist in a universe where matter and antimatter should have nearly canceled each other away. And the question will remain, what are we missing? This is why CERN is not only a machine, it is a symbol of a very human instinct, the instinct to go closer, to look deeper, to ask whether the world beneath the world is stranger than the one we can see. Above the tunnel, life goes on. Fields grow. Roads curve through the countryside. Clouds move over the border between France and Switzerland. People wake, work, eat, talk, sleep, and dream. And below them, in the cold darkness, particles circle. They move almost as fast as light. They cross the underground ring thousands of times. They meet in tiny collisions that briefly recreate conditions far beyond ordinary life. The detectors listen. The computers decide. The data grows. And somewhere inside that data, the smallest clues in the universe wait to be understood. Perhaps the strange bee meson signal will become nothing more than a lesson in caution. Perhaps it will fade into the long memory of science, another ghost that looked real until the light became brighter. Or perhaps it will remain. Perhaps the angle will stay bent. Perhaps the number will keep leaning away from the rulebook. Perhaps, after all the checking, all the doubt, all the patience, scientists will find that the standard model has finally shown a real crack. And if that day comes, the announcement will not mean that everything we know is wrong. It will mean reality is larger than we knew. It will mean the universe has another layer, another page, another set of rules hidden beneath the rules that brought us this far. There is something peaceful in that thought, not frightening. Peaceful. Because the universe does not owe us simplicity. It does not have to fit inside the first map we draw. It can be deeper, stranger, more elegant, more mysterious. And still, slowly, carefully, patiently, we can learn to read it. One collision at a time. One particle decay at a time. One strange measurement at a time. Beneath Europe, the machine keeps listening. Not for a roar, not for an apocalypse, not for a dramatic sign written across the sky, but for a whisper, a tiny imbalance, a faint distortion, a pattern in the way a particle dies. And maybe that is how the next great chapter of physics begins. Not with something enormous, but with something almost too small to notice. A particle appears. A particle vanishes. A few fragments fly outward through the dark. The detector records their paths. The numbers are checked. The rulebook is opened. And somewhere, in the quiet space between prediction and reality, the universe leaves behind a clue. For now, the answer is still waiting. The signal is not a discovery. The rulebook is not broken. The mystery is not solved. But deep underground, where the magnets are colder than space, and the smallest things move almost at the speed of light, scientists are still listening. And the universe is still speaking. Softly, patiently, in particles, in patterns, in whispers beneath the dark.